and then share. This one. Okay. I figured out how to annotate. So I'm going to turn on the annotate and keep that handy. All right. Okay. So this chapter 16 is chapter 16 is on the topics are solubility and complex ions. I think the reason that both of those are placed together in the same chapter, even though solubility involves a precipitated compound, it's a solid, and the reaction is the dissolution of that solid. Small amounts, although they may be, go into solution. But for complex ions, there are no solids involved. You have the individual ions, and then they come together. Well, yeah, the individual ions, and then there's a ligand ion, which I'll explain later, that attaches to one of those ions and keeps it in solution. Now, I said there were no solids. In the formation of the complex ion, there are no solids, but there's always a solid involved. I guess I should get into the topic because I'm digging myself deeper. Okay, chapter 16. And that's not what I want to do. There we go. So, like I said 3 chapters ago, equilibria is going to be a recurring theme. And there will always be a K involved. But in this case, the K has a subscript of an SP, standing for solubility product. Now, from math, you know that a product is something times something else. And that's appropriate for this K value. And we'll use this example. Bismuth sulfide. When we place it in, and invariably we're talking about aqueous solutions. There's Isaac. Okay. We're talking about aqueous solutions. This solid, bismuth sulfide, will, to a limited extent, supply ions into solution. The bismuth 3+ and the sulfide 2- ions will be in solution, and there will be an equilibrium set up between the two. So, Steffi, okay. Now we're rolling. So you'll recognize a reaction in which you have reactants and products, and of course when you derive the expression, of course it's got powers, and then the tendency is to put this one in the denominator, but since it's a solid, and this is characteristic of all the solubility product expressions, there will be a solid involved which drops out of the expression, and the only thing left is the numerator, right? So you always write the solid on the, as a reactant and the ions as products. And the expression then becomes a mathematical product of one ion against the other one. It could be more than one, right? If you have a compound, a solid compound that breaks into more than one ion types, there could be three or more. But we're going to try to keep it simple. And we have these two as products, so that's why the solubility product. And the next, of course, you're familiar with the equilibrium constant. Of course, the only thing that'll make that change is temperature. But there's a difference between solubility product, versus solubility. Solubility or product refers to the constant. That never changes as long as the temperature doesn't change. But the solubility does change depending on the environment. And the fact that KSP is higher just means that at equilibrium, you have more ions for that reaction in solution than, say, some other competing reaction or comparing reaction. But the solubility refers to how much of that solid goes into solution. And if you look up the values for solubility in the literature or in any handbook, there'll be something like so many grams per 100 mils of water. That's usually the way they express it. Now we're going to, when we talk about solubility here, we're usually going to define our solubility in terms of molarity. Right. So how much of the bismuth sulfide goes into solution? And that will vary depending on the environment. Right. For instance, are there common ions involved? Right? Is it not just pure water? There could be other ions there in solution, and they may be there for a purpose. Right? You may want to limit the solubility. So you put a common ion in there that will force the solubility back. Or you have a coupled reaction that's going on at the same time as your solubility that helps drive either drive the solubility back toward the solid, or it may enhance the solubility to increase the amount of the solid that goes into solution. Right? So solubility and solubility product are two different concepts. They're related, but they're different. They're the same, but different, right? Okay. Now, in this example, we're saying the solubility is expressed in terms of mass per unit volume. Okay, I'll go with that. You can express solubility in a host of different ways. But whereas the solubility product could have a whole range of possible units involved. That's why we don't, this is an equilibrium constant, so we don't mention the units. But for solubilities, we generally do say how soluble is it? How much of it goes into solution? And the other factor that you have to consider is these powers, right? they affect the value of KSP significantly, whereas solubility is not hindered by those. It's calculated using those powers, but the powers can very easily make this value be very small and this value be reasonably large. Right, so you've got those considerations to haunt you when you do these calculations. So let's take an example. Let's say that we have silver chloride. All right. So we're going to write silver chloride as a reactant. Okay. And in aqueous solution, it would dissociate into these two ions. Right. So there's our expression. There's our reaction, and it's balanced. And then if we write the solubility product, we just have these two to the first power. And that's equal to 1.6 times 10 to the minus 10. Okay, so this implies, and this is characteristic of nearly all solubility products, they're going to be small numbers. If something is exceedingly soluble, like sodium chloride, the solubility product has no meaning, right? Because all of this turns into that. Right? So I mean, you can write a solubility expression for a completely soluble compound. That's valid. Is that normally we deal with solubility products in terms of what we normally consider insoluble compounds, right? If you use that chart, well, I don't have a handy one, where you have the cations down one side and anions, no, the cations across the top, anions down the left, and you find out where they intersect, and that tells you their solubility. That chart would say that silver chloride is insoluble, right? But that's insoluble in quotes, right? Because now we're saying that some of it does go into solution. Not much, but a measurable amount is in solution. And that's important because if we couple any other type of reaction, then the chemistry doesn't work unless you know or assume that there is some of it there in solution. And we're going to look at one of those later when we talk about complex ions. Okay, so now back to the problem. Here we go. So there's our equilibrium expression. That's what it looks like. Now, where do we get this expression? This is an abbreviated version of the ice table, right? So if you have this here for our ice table, right? You start off with a certain amount of that, but it doesn't enter into the equation because it's a solid. So there's no value there. But some of it does go into solution. And initially, we say if we're going to put it in aqueous solution, pure water to start with, then there's nothing there to begin with. But some of this goes into solution and produces that. Right? So now you just have the X and the X that go into your calculations, and that's where you get the X times X is equal to this value. Okay? If this were an expression with powers involved or exponents here related to the coefficients, then you would have values there which would be powers of X. Okay, so this is a fairly simple solution, because you just have x squared equals this, so x equals the square root of that value. X equals 1.3 times 10 to the minus 5 molar, which means if that's 10 to the minus 5 molar, where did it come from? Well, it came from here. So the solubility at that temperature in pure water is 1.3 times 10 to the minus 5 molar, or moles of silver chloride per liter. Okay, so this expression of solubility is not in terms of mass, but in terms of moles. Right? If you want to know mass, it's simple. Right? You just use the molar mass and do the conversion, and you can find out what the solubility is in terms of grams. And you may need to know that, right? If you're trying to make a solution, then you would want to, or, well, I'm chasing a rabbit down a hole, so let me cancel that argument and let's move on. Okay, so what about this one, silver phosphate? Let's try that one. Okay, so let me just erase these parts. And we're going to have a different equation up here. First thing you need to do, this is a word problem. It just tells you the name of the compound. So that's why in Gen Chem 1 and in Intro to Chemistry, I always hammer nomenclature. Because if you don't know nomenclature and how to go back and forwards between names and compounds, then you might as well just give up and go home. So, silver phosphate. Right? So phosphate is a complex ion. It's a -3 charge. Silver is a 1+ charge, so you need 3 silvers, right? So there's your compound. Now we can write the rest of the expression, because this is a solid. So you're going to have 3 silver ions. I'm going to leave the aqueous out because I'm running out of room. And you have 1 phosphate. Okay. Now our expression becomes to the 3rd power, and then phosphate. There you go. So there's your expression. Now, what would the solubility expression be? Well, let's see. We've got to put this value in there. 1.8 times 10 to the minus 18. So if we look at the ice table, right, so you're going to have, for every one of these that comes from that one, well, you have 0 to start with. You'll have that much for this one, but you're going to have 3 times that much for this one. Okay? So at equilibrium, you're going to have 3x and then x. So you just plug these values in, 3x for this one, to the 3rd power. And this one is just x. Okay? And that's equal to this value. So if we resolve this expression, we get 3 to the 3rd power, which is 9. And then x to the 3rd power times x, which is x to the 4th. Right? And there's several problems in the review document that have you do exactly that calculation. In fact, there's a whole bunch of them. So this expression is equal to that value. So when you set that equal to this one, you divide 9 into that, and then you take the 4th root of that product. quotient. Okay, and when we do that, we should come up with that value. Now, what does that mean? That means that 1.6 times 10 to the minus fifth moles of that solid go into solution to produce that in a liter. Okay. Now, we can say that it's that many moles of this because of the ratio of this to that, right? There's one of them here, there's one of them there, so that X value is the solubility. Oh, Kessa.
I can't stay long. I'm on like a break at work, and I wanted to pop in and see what I was missing.
Okay. Yeah, we'll
I'll probably be here for maybe like 10 or 15 minutes.
Okay. Solubility is the topic right now. So it's important in this case to pick your X. If this is 1 and that's 1, then that X is the solution to the problem. But if you choose X for this one, that makes this one 1/3, then the X is not the answer. Then you have to do an extra calculation to find out what the solubility is. So the answer that you would get in that case, you would take 1/3 of it. That's just a word of caution. If you pick your X correctly, then X will be the answer. Okay. So now we're entering into common ion territory. Let's make some room here. Now, when you did the Le Chatelier's lab, there were several reactions in there that were coupled. You could separate them into different expressions, but they were connected by one or more ions. So that's where we're headed. That's the territory. So we want to know, does the solubility of silver chloride change in a solution that's acidified with nitric acid versus what it would be in water, right? So we know what it is in water. We've done that calculation. And we found that the, let's see, the KSP, I might have to back up. KSP is 1.6 times 10 to the minus 10, is it? And the solubility, and in your book, and I think in the review document, we use a small s for solubility. Right? So the solubility for this in water is 1.3 times 10 to the minus fifth molar. Okay, so that's aqueous. Now what is it in oops, I'm getting ahead of myself. Back up. Okay, so there's this reaction, and in the same solution, you have this reaction going on. Okay. Now, technically that's correct, but we know that nitric acid is a strong acid, so it's completely dissociated, right? So the only ions, the only components of interest in this solution are these two, right? That one doesn't count because none of it comes back that way. Okay, so what do we have to deal with? Well, we've still got some of this solid. We've got some of these, small amount of these ions, and we have some of those. Okay, so how are they going to interact? We can speculate on different reactions that could occur, right? Hydrogen and chlorine, we could get that reaction, right? Is that going to work? No, because hydrochloric acid is strong. So this one does not, that has no bearing. Well, how about the other one? Silver and nitrate. Okay, how about that reaction? Well, if you look up silver nitrate in any handbook or in any of the handouts or in your textbook, you find out this is completely soluble. So that reaction doesn't have a bearing. The only reactions that have a bearing on this solubility are the ones that tie up either one of those ions. Right? According to Le Chatelier, if we remove one of these ions, then it makes this more soluble. It draws more of it into solution. But we've just shown that none of the possible reactions will remove either one of those. Right? Cation, anion has no effect. Right? So the solubility of silver chloride in this acidic solution that's made by adding nitric acid, the solubility is the same in both solutions. Okay? There are no common ions that remove either silver or chloride from solution. That's the only way that you can increase the solubility of silver chloride, is tying up either one of those ions. And we haven't done it with this scenario. Okay, so let's see, we've got this one. Let's look at another possibility. All right, how does the solubility of silver phosphate in water compare? Okay, so we've got a different reaction. This is going to be phosphate. There. There. And phosphate. Our polyatomic ion. There we go. So let me back up and get the right numbers. Oh, they might be here. Let me check. No, they're not there. I want to put actual numbers here. Phosphate, 1.8 times 10 to the minus 18. And the solubility in water we found to be 1.6 times 10 to the minus 5. Okay, now we can go ahead. There we go. Okay. So we have this reaction, and then we've got nitric acid that we put in solution. All right. Now, if we combine those two reactions, then we get this one, that one, and we have these ions over here. Now, do any of those ions interact? Well, let's say silver And phosphate, of course, we already identified that one. How about hydrogen and nitrate? Well, that's not work. No, silver and nitrate. Well, I don't see anything. Ah, okay. So there's some information here that is not given by those equations. We know that phosphoric acid, which is, if we combine this one and that one, we know that O4. HPO4 2 minus. We know that this reaction is very heavily weighted in that direction, right? Because when we looked at the equilibrium expressions for phosphoric acid as it deprotonates, it goes from H3PO4 to H2PO4 minus, and then H2PO4 minus, and then HPO4 2 minus. We find that is less and less dissociation as we go down. So this reaction is going to be driven to that product. So what we're doing is we're removing this polyatomic and making an intermediate to the dissociation of phosphoric acid. So what that does is it effectively removes phosphate from the solution and drives the reaction that way. So we have, by that logic, increased the solubility of silver phosphate. Another way of putting it is, if this is a strong acid, H2PO4 minus, and then this one dissociates into HPO4 2 minus, right? So this, with this being a strong acid, this is slightly weaker, but this is still a very strong base. And what is it going to do? Well, as the phosphate is picked up by this proton, then any other protons in solution are also going to react with this product and drive it back to here. Okay, so you actually won't have a lot of that in solution because it's going to be driven back toward this one. Okay, that's a strong acid, so it's going to all end up as this ion here, and it'll keep going until all of this is used up. Right? So if you put more acid in the solution as nitric acid, it will continue to dissolve that. So let's say you reach an equilibrium state and you still got solid in there. Well, just add some more nitric, like a drop or two, and stir it around and see how much more disappears. Eventually, if you keep adding hydrogen ions, you're going to drive the reaction completely to the right. You're not going to have a lot of phosphate in solution, right, because it's used up, but you will have silver in solution. Okay? I'm just pausing for expressions of confusion. If you guys are good with that explanation, we'll move on. Okay. So how does the KSP of silver phosphate in water compare to the KSP of silver phosphate in acidic solutions made by adding nitric acid to the solution? Well, we just explained it, but we didn't quantify it. The KSP, of course, is the same. What we didn't, the previous slide, the solubility would increase, right? But the KSP of phosphate in aqueous solution does not change. It's a constant. What we have changed is the solubility, right? So this is aqueous solution only. That value would increase. And it all depends on how much acid you add. And it can be quantified. We can do our equilibrium ice table and determine how much more of this will go into solution or what is the new solubility. But it's all based upon this KSP, which is constant as long as the temperature doesn't change. Okay, so now we're going to do an example. Calculate the solubility of silver chloride in this solution to begin with. So there's your KSP for silver chloride. Here are the conditions: 100 milliliters of 4 times 10 to the minus third molar calcium chloride. So we would expect that the addition of this chloride ion would do what to the reaction? I'll let that sink in while I prepare the whiteboard. All right, so we're going back to silver chloride now. And this is 1.6 times 10 to the minus 10. And the solubility in, let's see, do I put it in here? No, I didn't. Well, we're going to calculate what the solubility is. And we're given 100 mils of solution, which also has a concentration of calcium chloride at 4 times 10 to the minus third molar. So calcium chloride is 4 times 10 to the minus third molar. Okay? So, our ice table then would be set up so that we have initial change. So what's the initial concentration of silver? Well, it's 0, right? Because we start off with the solution, but we haven't added any silver chloride yet. So when we add the silver chloride, we're 0 here, but we do have a significant concentration of chloride already in solution. So how much is that? Well, if this is the concentration of the compound, what's the concentration of the chloride ion? It's twice that much, right? Because you have 2 for every 1. So this is going to be 8 times 10 to the minus third molar. Right? Initial. Now, since there's no silver in solution to start with, we're going to create some. We know that the reaction is moving that direction. We just don't know how much yet. So, at equilibrium, we have that much, and X turns out to be equal to S, the solubility, because it's 1 to 1. Right? So we chose our X correctly. And then this is 8 times 10 to the minus third molar plus X. Okay? So there are two terms that go into the expression here. There you go. Just plug those in there and solve for the X or the S. And that's what we've done here. We've also assumed that because, let's see, here we go. Because X is going to be very small, we know X is going to be very small. We've already shown that. It's going to be very small in relation to this value. Right? Now, if this value was very close to the previous solubility calculation, what was it, 10 to the minus 5? Well, we can make that assumption rather than solve a quadratic and then do our 5% calculation. It works for this one as well as any other equilibrium. But I'm asking you to take it on faith. It is within 5%. And if we take this at face value, then that 10 to the minus 8 is much, much smaller than this one. So it should be within the 5% rule. And we just solve for the X, and that the way we've chosen X says that X is the solubility. Right? So the solubility is a lot less by adding that much calcium chloride. And the reason it's less is because we've added some common ion. We added some of this. So it's less, any silver that dissolves in solution is going to be absorbed in the reverse reaction. So when we reach equilibrium, there should be less of this. Okay, so how much chloride is left in solution? Well, there should be the same amount of silver as there is chloride once the reaction is complete. Right? So it should be 2 times 10 to the minus 8 molar of chloride as well. So we've used up quite a bit of this initial chloride in the process. No, that's not right. Because our expression says it's 8 times 10 to the minus third plus X. So the chloride concentration hasn't changed much at all. Okay, I misspoke. When we add this plus this small amount, we basically have the same concentration of chloride as we did before. But we have a lot less silver than we expect in pure water. Okay. Did I confuse anybody? If this reaction were by itself, then the silver and the chloride concentration would be the same. But since we already have chloride in solution, and this is the expression for the chloride concentration, then the chloride concentration hasn't changed much at all from the added amount. Okay, and this is just a note. 100 milliliters doesn't matter because you're already given the concentration. That's just blue smoke. What about the solubility of silver chloride in 100 mils of calcium nitrate? All right. So what's happening? Calcium nitrate dissociates. It's completely soluble. Let's see, this should be 2. Plus 2 nitrate. Here we have a similar situation to the nitric acid, right? The nitrate plus silver is soluble, no effect. Calcium and chloride, completely soluble, no effect, right? So the solubility in calcium nitrate solution should be exactly the same as pure water, because there's no common ion to affect the reaction. All right, and that's just recalculation of the solubility. 10 to the minus 5th molar. Okay. Now, suppose we go the other direction. Rather than adding the solid to the solution and watching it dissolve, suppose we mix soluble ions together, and we want to know, do we get a precipitate from it, right? Can we calculate or even intimate from values that we can get from the concentrations that are given, whether or not we will produce a precipitate of some type? Now, the reason this is important is that wet chemistry methods exist for separating metal ions that are in a mixture, in a solution. And if you know their KSPs, their solubilities as a result of that, and you know their concentrations, then you can calculate a Q value using the concentrations and compare that Q to the K. If you do that, then you can draw these conclusions. If the Q is greater than the KSP, that means you've got more on this side, right? More on that side than you would have at equilibrium. So you're going to get some of it to precipitate. So if the Q is larger than the K, then you would expect some of the ions to precipitate into the solid. If the Q is less than the KSP, then you will get no precipitation, no solid form. So that's just this is the expression that you would compare. Right? If you compare this one, actual values to actual values here, compared to the K, then you would find out whether or not you would expect a precipitation. If the product of the concentrations is greater than 10 to the minus 10th, you would expect to produce silver chloride solid. Okay. So that brings us to the topic I alluded to earlier, selective precipitation of metal ions from solution. So the general concept is you add a reagent to the mixture that obviously has to be soluble, and there is a common anion in there that binds with the metal and forms a precipitate. Now, if you only have 2 ions, it's fairly simple, right? If you add sodium chloride to this solution of barium and silver ions, then the chloride and the silver are going to combine and produce silver chloride, solid. And leave barium behind because barium chloride is completely soluble. Right? So that's the simplest scenario, where one reacts with the anion and the other one does not. In that case, you don't even have to calculate a Q value. But what if it gets a little more complicated? Say you have copper 2+, mercury, 2+, nickel, manganese. What would be the effect of using hydrogen sulfide? Well, this is very dependent upon the pH. So at low pH, the concentration of sulfide ion is relatively low. Why is that? Well, let's look at the reaction for hydrogen sulfide. In solution, all right? So all of these are in solution. Okay? Hydrogen sulfide can be in solution, but it's molecular on this side. On this side, it's dissociated. So what if you're in acidic solution? That just means that you've added a lot of protons. And of course, you choose an acid in which the counter anion does not react with any of your metals. And nitric acid is a very good one to choose because all nitrates are soluble. So if we add nitric acid here, what does that do? Well, that drives the reaction back this way and decreases the concentration here of the sulfide. And the sulfide is the anion we want to react with the metals because it's the anion. So you look at the sulfide solubility products for each of these metals, and you find that if this concentration is very low, you're going to be precipitating only the metals that have a very low solubility product for the sulfide. So like this one or this one, their KSPs are very low, extremely low. So very small amounts of sulfide in solution will give you a Q value that exceeds the KSP. Right? But it's not, the Q values are not high enough to precipitate the other cations. Right? See the relationship there. If we can make this very low, then it only precipitates the ones that have a very low K value. Okay, that's the beginning of our selective precipitation, or selective, selective precipitation of cations from solution. Now what happens if after what do you do when you get these in solid form? You filter the solution, right? You take them out of solution. And then what's left over, the filtrate, you take the filtrate and now you add hydroxyls. Like you want something that is completely soluble with any of the other anions that might be there. Sodium hydroxide is a good choice and a cheap choice. So if you add hydroxides, then now you're going to remove, right? Hydroxide is a very, very strong base. It will pick up those protons and make water and drive the reaction this way. What does that do? That produces lots of sulfide ions. Now with the sulfide ion concentration high, your Q value is elevated to the point where it exceeds the K value for the other metals and nickel. Right? So now the Q exceeds the K for these two, and they precipitate. So you've managed to separate copper and mercury from the solution, and now you have precipitated nickel and manganese. And you can filter the solution. Now you have those separated. So you can see if your solution is extremely complex with a dozen or more cations, then the process of separating them can be very tedious and very time consuming. So that begs the question, how do you know that these are even there? Well, you take a small sample of them and do a qualitative analysis to find out, are those ions there? Right? And there are methods for doing that. All right. Let's see. Let's make some more room here. Okay. So this is what actually happened when we did the work. Say we were in the lab and we did those precipitations. You add acidic hydrogen sulfide, pH of 2 or even less, which produces very small amounts of sulfide. So that selectively precipitates copper and mercury. So here you go. Filter it out. Then you add a base to a pH that's in the alkaline range, right? Greater than 7. And now you've increased the Q to the point where you can precipitate these two. So that's your separation. This, I guess you could call it a decision tree or a process tree. Well, here's another one, a little more complicated. Say you have all of these ions in solution. Right? There's lots of them. How do you get them separated? Well, you need to go through logical steps. And this is only a partial separation. And because the first thing you would want to do, you wouldn't want to go down here and add sodium carbonate right off the bat. Because what that would do is it would precipitate some of the metals that you don't want. I mean, it would defeat your purpose. So there's a logical step by step. So we divide these into groups. Group 1, 2, 3, and 4. And your review document has these things. I think I extracted these from your text. So you'll see them in your textbook. You'll see them in the review document. And I also have them in the folder for the exam. So you can call that up. You don't have to memorize this stuff. I mean, if you were going for a BS in chemistry at some university, yeah, they'd make you memorize this stuff. Right? So you're lucky. I'm giving you the decision tree. I just want you to understand the principle. So the first thing we want to do is precipitate chlorides. That's basically what we're doing here. Add hydrochloric acid, and we precipitate silver chloride. We've looked at that one. Mercury 1 chloride will also precipitate. Let's see. There's a 2+ mercury. Here's a 2. Oh, this is a 1+ mercury. See, it's got an Hg2, 2+ ion. That is an oxidation number of +1. Okay. So this one we're going for in this extraction here. So this silver, the mercury 1, and the lead 2+. We'll get those three out of this mix just by adding the acid. And you filter it, you take the filtrate, and you go to the next step. So under acidic, right, we've already studied, under acidic conditions, if you add hydrogen sulfide, you get a very small amount of sulfide in solution. And now we're going to precipitate those that have very small K values for the sulfides. Right? And these are all of those from that mix that have very small K values for the sulfide. Then if we filter that, take the filtrate, and now alkalize it, add sodium hydroxide. Now we increase the amount of sulfide, and the next group comes out as sulfides that have higher K values for the sulfide solid. Right? Then what do you have left? Well, we've got barium, calcium, magnesium left. If we add sodium carbonate, which is soluble, then we've got this carbonate ion in there. And the barium, calcium, and magnesium, along with ammonia, are there in solution. Well, along with ammonia, potassium, and sodium. Right? So we've separated, all we have left is barium, calcium, magnesium of interest. And the carbonates will precipitate out by the addition of sodium carbonate. Sodium carbonate forms a basic solution anyway, right? So we're putting it in a basic solution, previously alkalized solution, right? Remember, strong base, weak acid, you get basic solution. So we're not changing the pH. But the carbonate goes completely into solution and reacts with the barium, calcium, and magnesium. So what does that leave us? Well, we're left with ammonia in solution. We can't analyze for sodium because we've added so much of it already. Right? So that's out. Potassium. We haven't added any potassium, so we could analyze this solution for potassium. Right? We would just have to separate it from ammonia. And there are methods to do that also. What we would probably do is distill it. And that's another step. So I won't go into that. But you could distill off the ammonia, capture it, and what's left in solution is sodium and potassium. Okay. So that's the logical sequence of separating ions. Now, once you've got these solutions over here, you've got to go through additional steps to get them separated. Right? So the show's not over. If you're a bench chemist and you're charged with the task of separating all these ions, you've got a tall order. And not just the additional steps, but every time you conduct an experiment or procedure in this tree, you're not 100% efficient. Right? You're going to leave some behind, hopefully very small amounts. But the recovery of the metals, based on what you started with, it could be very low. Right? So you need to have a good technique, and you need to have a lot of solution if you want a significant amount recovered. Now, if you're just trying to determine the concentration of these ions, well, you can't determine the concentration of the ions easily by alternate methods, but you can determine the concentration of the metals in solution. There are spectroscopic methods that work very well. We used to do it with inductively coupled argon plasma spectrometry. Right, so that's a big name for a hot plasma flame that ionizes all of them and then reads the spectrum as the electrons return. Right, and you can quantify them that way. But if you actually want to, that just tells you how much is there. If you actually want to recover them, then you're stuck with wet chemistry. Okay. Now let's talk about complex ions. What is a complex ion? All right, you need a metal ion as the central. It's in the middle, some metal ion. It may be +1, +2, +3, whatever, but it's a metal ion. And then you react it with and in a solution that provides ligands. And ligands are those that it could be 2, 3, 4. I've seen up to 12 ligands attached to the metal. Sometimes water molecules will attach. Sometimes ammonia molecules will attach. Those are just two examples. So what does that mean? That means that this metal is soluble now, and it stays in solution. So if we had something like this, and we wanted to increase the solubility of silver chloride, all we need to do is remove, well, one way of doing it is to remove these silver ions into a complex ion whose equilibrium is far to the right. So the silver becomes complexed, and Le Chatelier says the more you remove, the more soluble the silver chloride. So the constant that's involved here, for instance, if we have silver ions and we want to complex them with ammonia, right, and it's in solution, it'll take 2 of them and produce this ion, which is also soluble. All right, so what we've done is we've tied up that silver in a different soluble compound, and these are parallel, what's my word? Coupled. These are coupled reactions, and they're coupled by this common ion here. Okay, now you can write an expression, an equilibrium expression for this equation, right? So this would be a formation constant. So in a formation constant, the complex ion is a product, and the metal and the ligands are reactants. So you would have an expression here of this one on top and these on the bottom. 2. Okay, so that's your expression. Yeah. That's your equilibrium expression for the formation of this complex ion. Here's some other, this is another different example. Right? For the formation of a complex ion using beryllium and fluoride ion. So all you would need to do is just add something to the solution that is that supplies the fluoride ion, but has no common ion effect, which would influence the solubility of your beryllium compound. Right. So, what do we have? Well, the complex ions form in stages. Now, I wrote this one in terms of 2 ammonias attached to that 1 silver, but it happens in stages. Right. This is the overall formation constant for that reaction, but it's actually a combination of reactions in which 1 ammonia attaches to the silver, right, and produces that compound, and then this one is reacted with another ammonia, to produce the final. So this is the overall formation constant. Now, why do we bother those intermediates? It's to explain what happens in stages. It's kind of like acid dissociation, one proton at a time. These reactions occur one ligand at a time. But we're only interested in this one because, look, even though we attach one fluoride at a time here, look how large the K value is, extremely large. So you're going to start off with this one, but then that one attaches another fluoride, and this is large. So what happens to this? Well, practically all of it is converted to that. So then we add another fluoride, and this one's large too. So we get all of that. And this one's relatively large. So we actually end up with, from here, with 4 fluorides to here. Okay? And how would we combine these equations? We just use Hess's law. Right? So if you add all these together, notice that this one cancels that one, and this one cancels that one, and this one cancels that one. So you have this one, 4 fluorides, and this as your product. And then what do we do with the K values? Well, when you combine equations, you multiply the Ks. So this one times that one times that one times that one, which gives you a huge K value. Okay? So the whole point of that argument is when you have large Ks at each step, you end up basically from here down to here. And these are just steps in the mechanism. Okay, that's one example. So let's say we want to dissolve a water-insoluble ionic solid. We're saying water-insoluble, we should put that in quotes, because we've learned in this chapter that everything is soluble. All ionic compounds have a certain solubility. It might be very small, but it's there. So there are 2 strategies. One is you look for an anion of the solid that is a very good base. What do we mean by that? Well, Lowry Bronsted base. If the anion in the compound, let's use this one as an example. Silver chloride. So there's your anion, right? Is that anion a good base? Well, let's look at where it would come from if it were sourced from an acid. That's a strong acid, right? That makes this a weak base. Right? So that's not a good candidate for acidification. Unless you choose the acid correctly. Let me put it that way. Because we've seen the difference between nitric acid versus phosphoric acid. But if the anion happens to be a good base, right? So that would be a poor example. That's not a good base. What if we have this one? Aha. Now, this is sourced from a weak acid. What's the weak acid? That's a weak acid. Now, H3PO4 is a strong acid. But by the time you get down to this proton, that's a weak acid. And we have a K value, a Ka value for this that proves it's a weak acid. So if this is weak, this is strong. Weak acid, strong base. So now, with a strong base as one of your anions, you can acidify that solution and increase its solubility. Okay, that's what this number one strategy refers to, is identify the base. That's a strong base, so it's a candidate for increasing solubility by acidifying the solution. Add more protons. Okay, that's one strategy. The second strategy is what do you do when you have this situation, right? You got a weak base. Well, now you can't attack the anion to increase solubility. You got to approach the cation. So in that case, you take the cation and try to get it into another form with a high K value so that it removes that from this reaction and drives the solubility that way. That's what the formation of a complex ion does. And in this case, our example was diammonium silver. Okay, and all they mean by stable complex ion is one in which the K value is very high. There are lots of complex ions that are not stable. They have very low formation constants. Okay. Let's wait a minute. Oh, we've got a yeah, we got time. We got a little video here. Let me see. My sound's as high as it can go. I hope your sound is better.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we get in part A to the solubility that we're going to get in part B. In part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water, and some of the silver chloride is going to dissolve, but most of it's going to stay in solid form. So silver chloride is only a slightly soluble compound. There's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver plus 1 cations in solution, and there are also chloride anions in solution. We have our.
You remember what saturated means? Saturated means that the forward reaction and the reverse reaction are equal in speed. The velocities both ways are the same. Okay.
Solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice statement. So our initial concentration, our change, and finally our equilibrium concentration. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product was 0. Right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride. We're going to call that X. So we're losing a certain concentration of our silver chloride. Look at our mole ratios. For every 1 mole of silver chloride that dissolves, we get 1 mole of silver plus 1 cations in solution. So we're losing X. Over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1 to 1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anion. So over here, we get a plus X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. I put in here 1.8 times 10 to the negative 10. And this is equal to, this is x times x, equal to x squared. So we can get on the calculator and solve for x. So we have the square root of 1.8 times 10 to the negative 10. Take the square root of that. X is equal to 1.3 times 10 to the negative 5. Round that. So x is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver plus 1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So not very, it's a very small molar solubility, so silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have 3 molar, right? We have some ammonia present. Now, what happens when ammonia is around silver cations, right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. Let's show what's happening. So we have a silver plus 1 cation. Right? We have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw one in on that side, and I'll draw another one in on this side. Remember your definitions for Lewis acid, Lewis base. Right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver plus 1 cation. Right? So ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver plus 1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right. This is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to become that silver ion and essentially remove silver ions from solution. So if we go back up here and think about our equilibrium, right? If we have ammonia present, we're going to be removing silver cations from solution, right? So we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present because of the formation of our complex ion. So if we added some ammonia, right? If we added a solution of ammonia here, we can get our silver chloride to dissolve, right? Because it's more soluble because of the formation of a complex ion. Let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound. We've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening. Right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right? We have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. We have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction. And if we added those two reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add two reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those two reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative third. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. We set up our ice table, so our initial concentrations, our change, and then our equilibrium concentration. And let's pretend like we're starting out with our solution of ammonia, and we haven't added any silver chloride yet. So let's go back up here, and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia, so let me put that down here. So our initial concentration of ammonia is 3 molar. If we haven't added any of our silver chloride, then we don't have any of our complex ions. The concentration, initial concentration of our complex ion is 0, and we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve. So we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia, so right, minus 2x. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing x over here, we'd be gaining x over here with the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1, so we're going to gain x for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x. Our concentration of complex ion is x, and our concentration of chloride anion is also x. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion. And we raise the concentration to the power of the coefficient, so to the first power. This times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the first power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactants, over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is x, and our equilibrium concentration of chloride anion is x. So on the right side, we would have x to the first power times x to the, take that out, times x to the first power, right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third, so 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. Let me write this out. We would have x squared over the minus 2x squared is equal to 2.9 times 10 to the negative third. So what we could do here, these are both x squared, right? These are both x squared, so we can just say that this is all squared on the right side. Now we can take the square root of both sides, right? So take the square root of 2.9 times 10 to the third, take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that, 2.054. So just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3. And if you round that, you're going to get about 0.16. And 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. So now we need to solve for x. Right? So we've done our math here. So we have 0.16. And divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration, right? So this is our molar solubility. If we go back up here, x is 0.14 molar, right? So that's our concentration of complex ion, solution at equilibrium. That's our molar solubility of silver chloride, right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right? So in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
Okay, I know that took a while, but I thought it was a pretty good explanation. Sal Khan is a familiar voice, I'm sure, to some of you. Okay, so let's go to the next. And he's already described much of this in these slides. We take each step. So we've got this combined with that one, combined with the second addition of ammonia there. Right, so the overall reaction is on the next slide. Here we go. So you add those all together, you get that reaction which he Sal explained. And then, but when you add these together, instead of adding his composite with this one, if you add them individually, you get a slightly different number. His was 2.9, ours is 2.75, which is not far apart. One thing you'll realize if you haven't already in equilibrium expressions, the most important part of the value is the power of 10. And then you can refine it a little bit with the coefficient. But it's so approximating in the process that the power of 10 is the most important item. That's where your focus should be. One other thing, and this, all of this that we're talking about now is presented again in the laboratory for complex ions, which is the next one coming up. And this goes in one direction, doing the calculations as if you already know these values and determining what the you can determine what the chloride concentration is. But in the lab, we go the other direction. We use this equation, but we titrate the solution, the ammonia complex ion, with chloride, and actually calculate the formation constant for this compound. The formation constant will be the combination of these two Ks, these two right here. So if you multiply those two together, you would get an accepted value for the formation constant of this complex ion. And then when you do the lab, you actually calculate that value based on the titration. Okay, so that's just a juxtaposition of the two processes we're going through here. Another point I wanted to make. And I think this is also a supplement in the lab, right? So the lab document will have this as appendix at the end. So I won't go into the quantitative parts of it. But in order to form the complex ion, you've got to guarantee that the ammonia that you put in solution is still there when the silver goes in. Right, so we need to, and the appendix in the lab document will explain that the reaction that ammonia undergoes in water is this one. Okay? But the equilibrium constant for this expression is way over here. And I show you the calculation in the document that confirms that greater than 95% of the ammonia is still in that form. Okay, so it was just an exercise to prove that when we say the solution has 3 molar ammonia in it, when the stock is ammonium hydroxide, which would be this. Actually, what we're saying is it's that much ammonia. So in Sal's problem, he was 3 molar, and in this one that we're going to look at in these two slides, the concentration is 10 molar. Right? So we would expect that the solubility of silver chloride would increase as we add more ammonia to it. We do the same calculations that Sal went through, with the exception of 2.75 instead of 2.9. Then we end up with solving the problem for solubility, which is, we'll get there eventually. Right. So the solubility now is 0.47 instead of 0.14. Right. So the solubility, it goes up even higher with the addition of extra ammonia. All right. So that was the last, I think. Oh, this just adds a calculation. All right. How much of the ammonia is left? Right. So we just use the solution from our ice table and plug in the value for X, and we find that we've still got 9 molar ammonia left in solution. Right? So you can expect this solution is extremely basic. Okay. I don't know if we didn't go into naming coordination complexes. I I guess I could make a pun here. The naming of coordination complexes is very complex. But there is a method to it, and I've included a document. I believe it's in the same folder as the PowerPoints. If you're interested in learning about the naming of coordination complexes, but I'm not going to make that a requirement for this course. Actually, I've seen coordination complexes named a couple of different ways. So there may be a standardized way, but there's also probably a trivial way to do it as well. Okay, any questions? We're finished way ahead of time today. So we've got, you guys have several labs that are pending. There's only one of you is current on submitting labs, which could be a problem toward the end of the semester. We're already past the midway point. And at some time in July, I've got to start preparing for fall. So that's going to put a crunch on my time and the ability to grade your labs. So the sooner you get them in, the better. Everybody, except for one student, is up on their homework. And let's see, exams. Okay, we've got the exam today on acids and bases. Is not due till midnight. So you've got time on that one. Okay, any questions? I guess everybody's okay with the topics. And this is Thursday, so next Tuesday we'll do a review on complex ions. And I think, let me be sure, I think I've got, no, I still have to upload the complex ion lab, the video. I think I already have a video on it, but I'm going to check it to be sure because it may need some tweaking, or I may have to re-record it, depending on the quality of the video. Okay, is everybody good? I see two faces. Okay, a thumbs up, yeah. Is Isaac still there? Still there? Is Megan still there? That's not a good sign. Okay, that's my problem. If you got nothing more to talk about, we can call it a day. Bye-bye.